$40. That is the total cost of the PVC pipe sitting in my backyard right now. Not $40 for a component. $40 for the core of a system that is pulling heat straight out of the ground and pushing it into my house tonight, with no furnace running, no combustion, no refrigerant lines, and no monthly gas bill attached to any of it. And the part that stopped me cold when I first encountered this technology is that the physics behind it is not new. It is not experimental. It is not fringe. Peer-reviewed engineering papers going back to 1983 describe exactly how this works and exactly what it produces. Tonight I am going to show you the full system, the real numbers, the actual installation, and the one thing every YouTube video about this topic conveniently leaves out, because there is a catch. And knowing the catch is the difference between building something that actually works and burying $40 of pipe in a trench that does nothing. Let me set the scene first. Space heating accounts for 38% of all delivered energy consumed by buildings in the United States. That is the U.S. Energy Information Administration's own number from their 2020 Residential Energy Consumption Survey. 38%. It is the single largest energy cost in the average American home, and the conventional answer to that problem is a gas furnace, a heat pump, or a geothermal ground source system that costs, depending on who you ask, anywhere from $15,000 on the low end to $50,000 installed. Home Guide puts the average at $20,000 to $50,000. Energy Sage reports $15,000 to $40,000. And Concord Municipal Light Plant in Massachusetts, which actually tracks what their customers pay after incentives, says most residential ground source heat pump systems in their service area cost at least $31,000. These are not outrageous markups. Geothermal systems require drilling rigs, refrigerant loops, compressors, and certified HVAC technicians. The cost is real. But what if there was a version of this that required none of that equipment and could be built by one person with a rented trenching machine and $40 of PVC pipe from a hardware store? Not to replace a geothermal system. To pre-treat the air before it ever enters your house. And in doing so, dramatically reduce the load on whatever heating system you already have. That is what an earth-air heat exchanger does. And once you understand the mechanism, you will not be able to stop thinking about it. Here is the core physics. A few feet below the surface of the ground, something remarkable happens. The soil temperature stops following the air temperature. At the surface, temperatures swing wildly, minus 15 degrees Celsius in a Minnesota January, plus 40 degrees Celsius in a Phoenix July. But at a depth of roughly 1.5 to 3 meters, the ground reaches what engineers call the undisturbed ground temperature, UGT. At that depth, across temperate latitudes, the soil holds a near constant temperature somewhere between 10 and 23 degrees Celsius, that is 50 to 73 degrees Fahrenheit, year-round. It does not matter what is happening above. The soil at that depth is essentially a thermal battery that has been charging for millions of years, and it holds its charge through every winter on record. The USDA Soil Climate Analysis Network, which runs over 200 automated monitoring stations across the United States, has confirmed this consistently. The ground is warm. It is always warm, relative to winter air. And that temperature differential is a resource. An earth-air heat exchanger is simply a pipe buried deep enough to sit in that stable thermal zone. You pull cold outdoor air into one end of the pipe. The air travels through the buried section, the soil heats the air through the pipe wall, and warmer air exits the other end inside your building. No compressor, no refrigerant, no combustion. Just a small blower fan moving air through a pipe that the earth is continuously warming. That is the entire system. Now let me give you the name that most people in this space have never heard, because this is where the technology stopped being theory and became measured data. In 2003, a researcher named Girja Sharan at the Indian Institute of Management, Ahmedabad, published what became the most widely cited experimental study of a single-pass earth-air heat exchanger ever conducted. Sharan and his co-researcher, Ratan Jadhav from Sewa, Ahmedabad, built a test system using a 50-meter mild steel pipe buried 2.85 meters underground in Ahmedabad, India. They instrumented it carefully. They measured inlet air temperature, outlet air temperature, airflow velocity, and power consumption of the blower moving the air through the pipe. Then, they calculated the coefficient of performance, the COP, which is the standard metric for any heating or cooling system. A COP of 1.0 means you get exactly 1 unit of heat energy out for every unit of electrical energy you put in. A gas furnace in your house runs at about 0.9. A good electric heat pump runs at a COP of 3 to 4. What Sharan and Jadhav measured for their buried pipe in heating mode was a COP of 3.8. In cooling mode, 3.3. For a pipe in the ground with a small blower. That number was published in the Journal of Agricultural Engineering in India, Volume 40, Issue 1, pages 1 through 8. You can look it up tonight. And Sharan's study was not an outlier. In 2010, researchers Ozgener and Ozgener conducted an exergy analysis of a real Earth air heat exchanger system at the Solar Energy Institute in Izmir, Turkey. Their maximum daily thermal COP was 6.18. Their average COP across the measurement period was 4.74. A greenhouse cooling application they analyzed in the same year reported an average COP of 5.89. These are extraordinary numbers for a system with no moving parts except a fan. But here's the part I need you to hold on to, because this is where the story gets complicated, and where most people building these systems make a critical mistake. The Wikipedia article on ground-coupled heat exchangers, which synthesizes dozens of peer-reviewed sources and was last updated in March of 2026, includes a sentence that should be printed on the box of every PVC fitting sold in this country. Quote, "Earth air heat exchangers are best suited for air pretreatment rather than for full heating or cooling." And immediately following that, numerous systems have been designed and constructed improperly and failed to meet design expectations. Read that twice. These systems work. The COP data is real, but they are air pretreatment technology. They warm the incoming air before it enters your ventilation system. They do not replace a furnace in a deep, cold climate. If you live somewhere where winter air drops to minus 20 degrees Celsius and your undisturbed ground temperature is 10 degrees Celsius, your buried pipe can raise that incoming air by 30 degrees. That is genuinely useful. You are delivering 10-degree air to your heating system instead of minus 20-degree air, which means your furnace or heat pump is doing a fraction of the work it would otherwise do. But the output air is still 10 degrees. It is not 20 degrees. It is not 22 degrees. It is not the 68 degrees your living room needs. The soil gave it everything it had, and everything it had was 10 degrees. Knowing this distinction is what separates a system that delivers real energy savings from a system that leaves you cold in February, wondering what went wrong. So let me walk you through exactly how to design one that actually works, because the design details are where this technology either succeeds or fails completely. The first variable is pipe length. This is the most important number in the entire system, and it is the one the $40 figure completely ignores. A 50-meter pipe, like the one in Sharan's benchmark study, is roughly 164 feet. At current hardware store pricing, the pipe material alone for a 50-meter run of 160 millimeter diameter, PVC, which is about 6 inches, costs somewhere between $150 and $300 depending on your region, before fittings, before end caps, and before any inlet or outlet screening. The $40 figure is not wrong if you are talking about a very short test section, but a properly sized residential EAHE for a real home in a real winter is not a $40 project. It is a few $100s in materials, plus whatever excavation costs you in your situation, such as renting a trencher, hiring a machine, or doing it by hand over a long weekend. I want to be honest about that, because I respect your time and your money too much to pretend otherwise. The real story here is not that it costs $40. The real story is that for a few $100s in materials, you can build a system with a measured coefficient of performance of 3.8 that preheats every cubic foot of ventilation air entering your home all winter long. That is the actual value proposition. And it is a genuinely compelling one. The second variable is burial depth. Natural Resources Canada, the government's technical authority on EAHE design, published a document called Earth-to-Air Thermal Exchanger Design Principles and Concept Design Tool. It is the primary Canadian engineering guidance for these systems, and it is specific about burial depth requirements. You need to reach the undisturbed ground temperature zone. In most temperate climates, that means a minimum of 1.5 meters, with 2 to 3 meters being the range that most researchers and the Natural Resources Canada guidance consistently recommend. Sharan's benchmark system was buried at 2.85 meters. The 2018 study by Aliou and colleagues used a 38.5 meter galvanized steel pipe at only 1 meter depth, and their coefficient of performance came in at 3.2 with a temperature rise of only 3.4 degrees Celsius. Not enough for meaningful thermal comfort on its own. Depth matters. If your pipe is sitting at 60 centimeters because you did not want to dig deeper, you are not in the stable thermal zone, and you will not see the performance numbers the literature reports. Dig deeper. The trench is the hardest part of this project and also the most important. The third variable that almost nobody talks about in the DIY space is condensation management, and this is where things get genuinely ugly if you ignore it. When warm, moist soil air contacts a cooler pipe surface, or when warm, humid summer air enters a cool pipe, water condenses on the pipe interior. In summer operation, this is actually useful. The condensed water helps cool the air further. In winter, it creates standing water inside a buried pipe that, in the wrong conditions, can support mold and bacterial growth. The Natural Resources Canada document is explicit about this. They specify that the pipe must be installed with a continuous slope, a minimum of 1 to 2% grade, so that any condensate drains to a collection point where it can be removed. They also specify that inlet air should be screened to prevent insects and debris from entering the pipe, and that the system should include an accessible cleanout. If you seal both ends of a buried pipe, never slope it, never screen it, and never clean it, you are building a mold incubator underground and then pumping its air directly into your house. This is not a theoretical concern. The Wikipedia synthesis document notes it explicitly. The Natural Resources Canada guidance is built around it. Design for drainage from day one, or do not build this system. Now let me talk about the pipe material question, because this is the one that generates the most heated debate online, and the experimental data has a clear answer that might surprise you. Steel has a thermal conductivity of 373.2 watts per meter per degree Celsius. PVC has a thermal conductivity of 0.28 watts per meter per degree Celsius. That is a difference of 1,333 times. Steel is 1,333 times more thermally conductive than PVC pipe. By pure materials physics, steel should dramatically outperform PVC in heat transfer from soil to air. And yet, a June 2020 study published in Science Direct that directly compared PVC and steel earth air heat exchanger pipes buried at 100 centimeters depth found that the difference in outlet air temperature was modest. Not negligible, but modest. Why? Because the limiting factor in heat transfer for a buried pipe is not the pipe wall. It is the boundary layer of air moving through the pipe interior and the contact between the pipe's outer surface and the surrounding soil. The soil's thermal conductivity and the air velocity inside the pipe dominate the system's performance far more than the pipe material does. Which means PVC, for this specific application, performs closer to steel than the conductivity numbers alone would ever suggest. This is counterintuitive, but it is what the experimental data shows. PVC is also cheaper, more corrosion-resistant, easier to work with, and more widely available. For a do-it-yourself installation, PVC is the correct choice. Now here is the piece of data from 2024 that I want to spend a moment on, because it points toward where this technology is going and what the next generation of backyard builds might look like. In November 2024, a study published in Science Direct titled "Enhancing the Performance of an Earth-Air Heat Exchanger with Novel Pipe Configurations" reported on a numerical model, validated against experimental data, comparing straight pipe configurations against spiral configurations. The straight earth-air heat exchanger achieved a coefficient of performance of 5.94 in summer and 1.92 in winter. The spiral earth-air heat exchanger achieved 6.24 in summer and 2.11 in winter. The winter numbers are the ones I want you to notice. A coefficient of performance of 1.92 for a winter heating application from a buried pipe with a blower fan. That is still below the 3.5 to 4.0 range of a modern air source heat pump, but it is being delivered by a system with no compressor, no refrigerant, no mechanical wear components, and effectively zero maintenance cost. The performance gap between spiral and straight pipe configurations is real, and the spiral geometry achieves more soil contact per unit of trench length. This is not yet mainstream in DIY installations, but the engineering case for it is building. Let me also address the soil saturation problem directly, because it is real, and it has derailed more than a few installations. In 2014, a study on soil thermal saturation published in Energy and Buildings established something that seems obvious in retrospect but was not well documented before. If you run an earth-air heat exchanger continuously for extended periods, you deplete the thermal energy from the soil immediately surrounding the pipe. The soil cools down, or heats up depending on the season, and the temperature differential driving your heat exchange shrinks. Performance degrades. The solution the study found was intermittent operation. Run the system in cycles. Give the soil time to recover its temperature from the deeper, undisturbed mass around it. In practice, this means the blower for your earth-air heat exchanger should be on a timer or a smart controller that runs the system in intervals rather than continuously. 2 hours on, 1 hour off, as a rough baseline, though the optimal cycle depends on your specific soil type, pipe geometry, and thermal load. Continuous operation is the single fastest way to turn a high-performing system into a mediocre one. Design for intermittent cycling from the beginning. So let us bring this all together. You have a house. You need to heat it in winter. Right now, every cubic foot of cold outside air that enters your ventilation system enters at ambient outdoor temperature. Minus 10 degrees Celsius, minus 15 degrees Celsius, whatever winter delivers in your location. Your heating system has to lift that air from that starting point to 68 degrees Fahrenheit, 20 degrees Celsius. That entire temperature differential costs you money every single hour of the heating season. An earth-air heat exchanger, buried at 2.5 to 3 meters depth, running 50 meters of PVC pipe through stable temperature soil, preheats that incoming air before your mechanical system ever touches it. The soil does the first 20, 25, sometimes 30 degrees of temperature rise for you, using nothing but a small blower pulling a few dozen watts of electricity. Your furnace, or heat pump, or whatever you have, only does the remaining lift. The Department of Energy's own data says heating and cooling together account for roughly 35% of all United States energy consumption. Cutting even a third of your heating load through passive pretreatment is a meaningful number on an annualized basis. Not $40 meaningful, but a few $100s meaningful against a backdrop where geothermal alternatives cost $30,000. That is the actual value proposition, stated honestly. The technology is not new. The earliest references to moving air through or near the Earth for thermal exchange go back to ancient Persia and Egypt. Wind catchers and Qanat water channels that use the Earth's steady underground temperature to pre-cool air flowing into buildings. The wind catcher towers in Yazd, Iran are still standing. The tallest, at the Ahmedabad garden, reaches 33 meters. The principle has not changed in 2,000 years. The modern peer-reviewed literature formalizing it goes back to 1983, when Spengler and Stombaugh published their optimization study on earth tube heat exchangers for winter ventilation of livestock housing in the Transactions of the American Society of Agricultural Engineers. The technology transferred from agricultural buildings to residential applications through the 1990s and the 2000s. Santamouris and colleagues published foundational synthesis work through the Air Infiltration and Ventilation Center in 1995. De Peype and Janssens produced the first widely adopted European residential design methodology in energy and buildings in 2003. The engineering literature on this is 40 years deep. None of this is theoretical. None of it is waiting for validation. It is sitting in peer-reviewed journals that nobody in the HVAC industry has any incentive to hand you. What I am building here, and what I want you to walk away understanding, is not a replacement for a heating system. It is a front-end thermal processor for one. It is the difference between asking your furnace to sprint from -15 to +20 and asking it to jog from +10 to +20. The sprint costs money every single morning from November through March. The jog costs almost nothing. And the infrastructure that makes the difference is a trench, some fittings, a screened inlet, a properly sloped pipe, a condensate drain, an intermittent blower, and however many meters of PVC your lot can accommodate. Build it right, and it will run for decades with essentially no moving parts to fail and no consumables to replace. Build it wrong, wrong depth, no drainage slope, continuous operation, no inlet screening, and you will have an expensive underground mold problem that quietly poisons your indoor air quality all winter. The difference between those two outcomes is not skill. It is design intent. Get the design right before you dig the first inch of trench. If you are ready to go deeper on the full installation, trench layout, pipe sizing for different floor plans, blower selection, inlet and outlet configuration, and how to integrate this with an existing mechanical ventilation system, I have documented every step of my own build in the next video in this series. The soil here in my yard sits at 13 degrees Celsius at 2.5 meters depth in January. I know because I measured it before I dug. That is 55 degrees Fahrenheit of free preheating potential sitting underneath my lawn, available every single day of winter, waiting for a pipe and a small fan to put it to work. The ancient Persians figured this out with mud, brick, and wind. Girja Sharan measured it with instruments in 2003. And right now, it is running under my backyard for a few $100s in materials. The ground has always been warm. The question was always whether you knew how to reach it.